Good afternoon, everybody. We would like to get started, so if people can take their seats and fasten seat belts, then we can go. One of the nice things of being an AGU officer, and a section officer in this case, is to make sure that the people who deserve it get awarded. And today we have two specific awards. One is the Young Scientist Award, and we have the Gutenberg lecture, the annual named lecture of the seismology section. And I will start by introducing the awardee of the Katie Aki Young Scientist Award in 2009. And this year that was, again, it was a difficult choice. We had a large number of very highly qualified candidates, and that is very gratifying to see, so much young talent in our community. I should also say that the Aki Award was an idea that was conceived a couple of years ago by Paul Silver, who unfortunately passed away last summer, so cannot be here. This year, winner of the Katie Young Scientist Award is Florent Branguier of the Institut de Physique du Globe Paris. And he is now working at the Observatoire Volcanologique du Piton de la Fournaise La Réunion. And he has been recognized for his work for innovative studies of temporal variations of the Earth crust with applications to monitoring volcanoes and active seismogenic faults. And what you see here in this diagram is a very spectacular study that he was the lead author on, that came out last year in Science, where they used ambient noise cross-correlations to pick up transients or temporal changes in elastic properties, in this case the wave speed, over time associated with the Parkfield earthquake, and they associated that, or they correlated that with GPS and the intensity and frequency of tremors. And that is a very nice illustration of the kind of research that has been becoming very popular in the last couple of years, to use seismic noise and to, for imaging, characterization, and monitoring. I would like to make one interesting remark, is that Florent is a very fitting awardee of the Aki Award, because he has much in common with Kei Aki. Kei Aki, I think it's fair to say, was one of the first to use seismic ambient noise about 50 years ago, and that has, of course, been picked up by many, and including Florent. And also, Kei Aki, as many of you know, he spent the last years of his life in La Réunion, working on that observatory. So I'm very happy to call Florent to the floor to receive the award. Now this procedure, like last year, is going to be incomplete because something went wrong with the signing of the certificate. So, Florent, as I mentioned to you already, you will get your certificate, but not now. But congratulations. Thank you very much. So then I would like to welcome you to the 2009 Gutenberg lecture, and that will be given by John Vidale from the University of Washington, Seattle, on Tremor, the curious third wheel of fold motion. John got his undergraduate degree from Yale University, and to pursue his graduate studies he moved to Caltech, the best institute of technology, west of the Rockies, and where he actually got the Gutenberg Fellowship, and he worked under supervision of Don Helmberger on a range of seismic studies. And a couple of years later, with a PhD in hand, he made quite a tour through California. He started off as a research associate at the University of California in Santa Cruz, and then moved on to the USGS in Menlo Park. Then after a couple of years there, he went back to the University of California, but this time at the campus of Los Angeles, where he spent a number of years and has been very active in the leadership of the IGPP, initially as an associate director and later as an interim director. In 2006, he moved further north and to the University of Washington in Seattle, where he is now a professor and also the director of the Pacific Northwest seismographic network. And where he also started a new life, I guess, as Seismo Guy. Many of you will know his blogs, and that was quite interesting. His spatial moves from university to USDS and back to the University of California and to Seattle are dwarfed by his pathways through the Earth. John is an amazingly versatile seismologist, and I think he has worked on almost anything that you can think of. And also in terms of the regions of the Earth, he has covered most of it as far as I know. All the way from the inner core, both the structure and the rotation, through a very innovative approach using kind of a diffraction pattern of the inner core and see how that changes over time. He has done seminal work on the interfaces in the Earth, including the core mantle boundary and the upper mantle transition zone. Has worked on scattering in the lower mantle, has written a very widely used code for efficient ray tracing, worked on national hazards, and much more. And I think it's fair to say that he could have given this Gutenberg lecture on any of these topics, except maybe the ray tracing. That would have been a short one. But today he chose to talk about a particular aspect of seismicity on Tremor. And of course, seismicity is something that has been very dear to Benno Gutenberg. And if you go back to the very influential book by Gutenberg and Richter, The Seismicity of the Earth and Associated Phenomena, my guess what John could be talking about could be an associated phenomena, but at that time, of course, they didn't know about that. In contrast, if you read the introduction, and it's too small to read, but there's one interesting thing here, is that many well-observed and accurately located smaller earthquakes have been omitted from the study since they add nothing to the general information on seismicity. And they only crowd the maps and tables. So now, 50 years later, to the date, I'm not sure, but I expect to see quite a few maps that are crowded with small earthquakes. I hope that John can convince us that this is actually a new type of fault behavior with a lot of new information about seismicity. And the question is, is this new information actually consistent with the Gutenberg-Richter frequency scale? With that said, I present to you the 2009 Gutenberg lecturer John Vidale, and he will be talking about Tremor, the curious third wheel of fault motion. John, the floor is yours.
We're going to have to back up here a bit. Okay.
Yeah.
This really work?
Yeah, this is...
well, I should never start at the...
one more,
where
I
is
think.
that little... That's it. Hit that one. Okay, now we're at the beginning. Another great introduction. It's hard to live up to this. So the theme of this, as Rob alluded to, is the new kind of faulting that we've recently discovered in about the last decade, episodic tremor and slip, and this cartoon kind of captures much of it. Is there? Yeah, here's the time. And the cartoon version here is that shallow faults crack and rupture in a seismic way. Deeper faults may just flow, and that was our view maybe 10 years ago, and now we know that there's a richer, let's try that, undo that. Wow, this thing is pretty sophisticated. Okay, so now we can find a third kind of faulting in between these two. But I need to, and knowing I'm following Rob, I have to talk about Gutenberg. And so here's a picture of Gutenberg from the Scripps hallways. That's the guy in the top hat, very distinguished seismologist, of course. And I asked Rob, do you recognize the other seismologist? He's long tradition of tall Dutch geophysicists.
Well, not a seismologist, but Felix.
Yeah, exactly. Yeah. Good, Felix Andres. Oh, no, Wording Meinsing. The picture is just really to show his image. And from reading Leon Napoff's biography of Gutenberg, that's a hard screen to see, Gutenberg and Einstein were walking across the Caltech campus in the afternoon of March 9th, 1933. So deep in scientific conversation, they failed to notice the shaking of the ground in the disastrous Long Beach earthquake. So the lesson from this is that some important geophysical activities are not immediately obvious. And that's just like episodic tremor and slip, except it took us even longer to notice than magnitude 6.5 earthquakes. So let me go on to the table of contents here, and I'll talk basically about a detective story. What's happening during episodic tremor and slip, and I'll say right at the top that we aren't going to finish this story because we still don't understand it. I'll go through these list of topics. I'll talk about what's the tectonic setting of tremor, why do we think tremor is located where it is in these tectonics, and then talk directly about what tremor looks like, how it's regularly recurring in many cases and other times irregular. What is the magnitude frequency distribution, as Gutenberg might have posed the problem? How does tremor migrate over space and time? And how does a tremor respond to the stresses in the Earth? And then I'll talk about some dense array observations we made in the last year before we speculate even more. Okay. So this is the cross-section of a subduction zone. You can see the subducting Juan de Fuca plate, and we're looking at the Pacific Northwest specifically, and going under the North American plate. And I got this figure from Steve Malone, and the University of Washington, when I practiced this talk, they said I was getting carried away with my keynote graphics, but you'll just have to judge for yourself. And what we're looking at is the area between the locked subduction zone where it's shallow and where it's just freely slipping at depth. So this zone basically under the coast of Washington locally. And just to orient you, there's the deep earth. And this cartoon I've seen a half a dozen times today because we've had 3 full sessions of episodic tremor and slip. And it shows in more detail what I was talking about in the first cross section. So there's the very shallow is the accretionary wedge where maybe it's not even locked. And this is where episodic tremor is located. And still deeper, it's freely slipping. And in the shallower part, it's locked. So we can look at this in terms of the stress. This freely slipping parts on either side don't seem to have much stress. The lock zone builds up stress for a long time, 500 years around the Pacific Northwest, before it gets released. The episodic tremor and slip, on the other hand, seems to build up stress only for about a year before it's released. And I'll talk in more detail about how that works. And there's also an important issue of is the zone with this episodic tremor and slip adjacent to the lock zone, or is there some intermediate patch? So those are the issues we're dealing with. You can also look at this in terms of the motion along the fault. So there's steady motion in these extremes where there's low stress. There's no motion for a long time in the locked part, and every 500 years there's an earthquake. And in ETS, there's just a steady stair step of it locked, and then it moves for actually 2 weeks, and then it's locked for a year, and then it moves for 2 weeks. So that's the cross-section tectonic framework. Another picture I saw a lot of today also comes from Pacific Geoscience Center. And here the GPS measurements are these colored symbols arching upward. So green shows the ground compressing the stress in between big earthquakes. So it'll rise for 500 years. And this is 1996, and hopefully it'll keep rising well into the next century. And the blue dots are the actual GPS measurements. And the GPS measurements follow this trend, but they actually go up faster and drop down every year. And the point here is that they're rising faster because the ETS zone is locked, but then every year it lets go, and it's back on the long-term trend again. So it's just showing that the ETS zone is slipping in fact, precisely every 14.5 months. And then the black is the seismic observations, the tremor. And it's effectively the envelope of the 1 to 10 hertz seismic radiations. So what you're seeing is every time there's one of these drops where the ETS zone has released its stress, there's also kind of a rattling, one-to-one correlation. And you can also see the regularity of ETS. It comes along every 14.5 months, plus or minus a couple of months. And there are some more minor episodes we'll come back to, but the major episodes are regular. And this slow motion and the rattling, of course, are just two end members of the same phenomenon in general. This is an issue that's not just of scientific curiosity. This is a figure from the front page of the Seattle Times a little less than a month ago. And what it's questioning is whether the up-dip edge of the lock zone of the impending magnitude 9 earthquake is going to be here off the coast, so the entire rupture would be offshore, or if the near edge to Seattle of the lock zone is the red line. It's most of the way. You know, like a lot of newspaper stories, it's a little bit exaggerated, but there's a real uncertainty about the extent of the lock zone around the Puget Sound, and in fact all the way down to California along Cascadia. Another reason people are interested is the question of whether we can see the pattern of episodic tremor and slip change before the great earthquakes that neighbor the ETS zone. We haven't really seen a well-recorded set of ETS before a magnitude 9 earthquake, but if it evolves through the earthquake cycle, we'd always like to have some forewarning about big earthquakes. Another question is that the intraplate earthquakes, like the Nisqually earthquake in 2001, turns out to be probably not coincidentally located near the ETS zone. We'd like as much information we can about where those earthquakes under our coastlines are likely to occur. And third, the crustal earthquake distribution seems to be related again to the underlying ETS distribution. And of course, we're very concerned about crustal earthquakes. So it's a question of a lot of societal relevance. Unlike the Long Beach earthquake, this went unrecognized for a long time. This partly demonstrates why. If you just take a dozen seismic stations in an area that has a lively tremor, it looks just a lot like background noise, the wind in the trees or the waves on the coast or electronic noise. But if you filter this to the right passband, the tremor shows up a little more clearly, and what you see now is this high-frequency energy it's not coherent, but the envelope is somewhat coherent. You can see some of the same peaks from station to station, and you can actually see it arriving at different times. It arrives first on the stations closest to the source of the tremor, and later on the stations further away. This figure also demonstrates the character of tremor. This is a regular earthquake. This is some tremor. This is 5 minutes of record. And this is, again, the regular earthquake with a P wave and an S wave over a few seconds apart. And the tremor, this is, again, minutes of tremor, very different character. And the tremor doesn't just come as kind of steady, fluctuating humming, but there's also sometimes discrete pops. There's something we call LFEs, low-frequency earthquakes, which are just like a regular earthquake, except they take an order of magnitude longer to happen, have a different spectral content. There's events we call very low-frequency earthquakes, and now they take 100 seconds to happen, and which is orders of magnitude longer than other events of their magnitude. And there's ultra-low frequency earthquakes as well. So there's a number of phenomena associated with this episodic tremor and slip. This is yet another figure that showed up a half dozen times today. This one from the now classic Ide et al. Paper. It's a classic, but it really only appeared 2 years ago and was quite surprising when we first saw it. What it shows is regular earthquakes as a blue trend and slow earthquakes as the pink trend. The axes are the size, so the moment, which is just the area of faulting times the slip in the earthquake. And the vertical axis is the duration. Again, it's a logarithm, and this goes from 1/100th of a second to 10 to the 9th seconds, so decades. Each of these is, I think, 11 orders of magnitude. And the regular earthquakes their behavior has been known for a long time. They have a slope of 1/3. What that means is that the moment increases as the cube of the increase in the duration. And you can see this pretty simply. If you have an earthquake and it lasts twice as long, that generally means it has twice as long a fault and twice as wide a fault, and that the slip was twice as much. So it's 8 times bigger. So the slope of 1/3 comes from that relation of the cube, moment being the cube of the duration. These ETS-related phenomena, however, have a linear scaling. So if it lasts twice as long, it's twice as big. So it means the moment of the event is just accumulating steadily over time, whether the event lasts 1/10 of a second or if it lasts 3 weeks. Very surprising, and I have to say we still don't understand this very well. I'll probably say that a dozen times today. So structurally, the first question is, where does this tremor occur? I've shown seismograms on it, but it's not that easy to locate because there's not a sharp arrival, which is the way we locate earthquakes. But sophisticated techniques have been developed, led by Greg Burroughs' group at Stanford. And this particular plot comes from Justin Brown's GRL paper of the last year. And what he's done is taken recordings from Japan and these stations and projected the locations he finds onto a cross-section where the dashed line is the best guess at the location of the subduction interface. You can see all these different pops of tremor that he locates are indistinguishable from on the subduction interface and inclined with the right orientation. Other studies show it has the focal mechanism of subduction. It looks like this is just simple slip on the subduction interface. Just to make sure, he also looked at Vancouver Island in collaboration with a number of people. And again, if you look at the cross-section of tremor locations, it's planar, it's parallel to the subduction interface and indistinguishable from being on the subduction interface. And to be particularly thorough, he went to Costa Rica, worked with the group studying activity there with the SETA stations, and finds the same thing. The tremor locations are all right on the subduction interface within the uncertainties. So tremor seems to be activity mostly, perhaps not entirely, but mostly on the subduction interface. We can look at it in relation to other things with this plot, also from that now classic Ide paper. And this plot shows part of Japan. The dashed lines are the isodepth contours of the subduction zone. So 10 kilometers, 20 kilometers, 30 kilometers. And the purple outline indicates the zone inferred to have slipped in the 1946 Nankai earthquake. So this is the locked zone, currently locked. It's been locked for 50 years or more. And the red, yellow, and green symbols indicate ETS phenomenon. The red, each of these thousands little red dots indicate the location of low-frequency earthquakes. The yellow beach balls indicate the location of very low-frequency earthquakes, and the green squares indicate the location of silent slip episodes, which are slow phenomena lasting for days. And all of these are just down dip of the lock zone. So that's the relation that seems to be our working hypothesis. Okay? This is the first talk I've given in a long time where the audience can't interrupt. Might go a little faster. So when we first saw this, people were really puzzling why the Pacific Northwest seemed to have these jumps in the geodetic data and why Japan seemed to have this episodic tremor and slip, and pretty quickly people put it together. And rather than this being a unique sort of phenomenon, it turns out it shows up all over the place. They see kind of full-blown ETS now, both Japan and Cascadia. That's where we saw it first, but also Alaska, Mexico, Costa Rica. Now I'm probably forgetting a few places. There were a lot of exciting talks today of a range of regions. California now has many observations, many more than did just a few hours ago, to my knowledge, of both tremor that's kind of self-sustaining and tremor that's driven by stressing. Taiwan has triggered tremor, and New Zealand and Hawaii seems to have the slow slip, but perhaps not accompanied by the tremor. Okay? Oh, and I need to say here that I'll only be considering the kind of slow slip and tremor that's basically down dip of locked faults. One can also look at shallower activity that's a slow slip and perhaps tremor as well. Whoops, what's that mean? Okay. So the first guess people had is, if it gets too hot, we can't get tremor. If it's, too cold, we can't get tremor. But that isn't working out too well. This is a figure from a paper by Simon Peacock just a few weeks ago in JGR. And what he shows, first, is mineralogy is strongly dependent on the temperature and the pressure, the mineralogy in the subduction zone. And if we look at where the tremor is occurring, it's probably hard to read from out there, but in the Kai Peninsula in Japan, a tremor is in this region of temperature and pressure. In Shikoku, it's in this region, hotter. And under Vancouver Island, it's still hotter, but all in a similar depth range. So what this shows is there isn't just a simple range of temperatures, nor a range of simple mineralogy that's most conducive to tremor. We have to look either for other factors or more complicated combinations to explain where we're seeing tremor and where we're not. And maybe half the places we look carefully, we're not seeing episodic tremor and slip. and half we are. So in the search to find the explaining factors, this figure looks at California, and I first should say that one of the interesting characteristics of ETS is it shows up in a segmented way. The colors here indicate the, oh, you'll never be able to read this, how frequently the tremor recurs. So the red symbols are the tremor recurring down near California and southernmost Cascadia about every 8 months, quite frequently. The blue in central Oregon and southern Washington indicates the tremor here recurs less frequently, about every 2 years. And the white indicates it's on the order of every 14 months that tremor occurs in the Puget Sound and Vancouver Island, although not always spanning the entire region at the same time. So this segmentation can be explored in a number of ways, and here I should mention I just completely stole this figure from Mike Brzezinski and made it a little glitzier. And one way we can look for an explanation is just to see what's the velocity in the mantle. So this is, I believe, at 100 kilometers depth, the tomographic velocity. I think this is Richard Allen's tomography. And you can see that this region with the long recurrence times does kind of correlate with a less anomalous shear wave velocity compared to the regions north and south. And I won't explore this further, just mention that these are clues we might be able to understand someday. Another way to look at this is the geology of the ocean that's being subducted, because one could imagine ridges and blocks in the oceanic lithosphere might control the connectivity of the whatever's causing the tremor. And again, you can plausibly draw lines that correlate with changes in the patterns of tremor. That's work of Ray Wells. And a third thing one can do is look at the geology of the overriding plate. And this is from a paper by Dave Schmidt from last year, again, showing there are ways to try to explain the patterns from the crustal geology. And these all three may be related. So okay, I don't think we've closed the loop yet, but it's useful information. Something that's where the ideas have become more specific is relating the tremor to the cross-section. So in this case, this is a figure from Audette earlier this year. You can see the subduction zone, and this upper black line is the plate interface. The lower black line is the moho of the subducting lithosphere. And the model in this case, and these triangles indicate where the tremor is located. And the model that's been developing is that the oceanic crust, as it goes down, is full of fluids. The fluids are tending to come out of the crust, but for some reason are having trouble penetrating the plate interface. And this region becomes something where we clearly see low S-wave velocities and not so anomalous P-wave velocities consistent with high fluid pressure. However, when the subducting slab sinks still deeper, that pattern disappears, possibly because the material is fracturing as it's undergoing the phase changes from the increase in pressure of a subducting material, and then the fluid can escape. And it's this high fluid pressure that leads to the tremor. This same picture, drawn in more detail, can be seen in this. I've kind of heavily doctored this figure to simplify it, but it comes from the paper of Hirose et al. In JGR a year ago. And once again, we see this region. The red indicates very low shear velocities. I'm getting ahead of myself. I actually labeled these. Here's the moho of the overriding plate. Here's the plate interface, and they've located these with a range of geophysical measurements, reflection, receiver functions, as well as guided by the tomography. So this is as careful as one can be. This is the moho in the subducting lithosphere, and you can see the earthquakes in the subducting lithosphere tend to be in the subducting mantle, but our focus is really here. And with the lock zone up dip, the freely slipping zone down dip, and then the ETS region is coincident with the area with the low shear wave velocities and presumably the high fluid pressure. These blue crosses are the low frequency earthquakes. Those are more discrete pops, but still with the characteristic signature of ETS. Okay. And still a third picture. This picture is, a lot of people like it, although it's not a unanimous picture yet either. This shows a cross-section under the Pacific Northwest. Once again, the red is the slow shear velocity. The high fluid pressure is inferred to happen. All these earthquakes are tending to be in the subducting mantle. And in this particular case, I'd like to highlight these three stars, which are the three damaging earthquakes we've had in Seattle, the Squally earthquake and its predecessors in 1965 and 1949. And the argument can easily be made this is not coincidental, that these earthquakes are happening right where the high pressure fluid region is disappearing. That's why all these earthquakes are basically right under Tacoma. Once again, the tremor is right above the red zone. And this comes from a paper by Jeff Abers and his CAFE collaborators. And again, a figure I've taken from Mike Brzezinski, not really understanding it, but it seems to make sense. In Cascadia, we see the tremor coincides with the region of high conductivity, which is most easily explained by high fluid pressure. In Mexico, the same picture comes out. It's complicated, but basically there's a high conductivity region coincident with the tremor. And in New Zealand, there's not tremor that's been spotted, and there's not a high conductivity region. So people really like the association of high fluid pressure and tremor. Okay, so that's the tectonic setting, and it seems to be at least settling down a little bit. As we go through the rest of this, I'll talk about how the tremor appears. And this is, the observations are clear. And this is a picture of the one episode of tremor activity under the Pacific Northwest, specifically the segment under the Puget Sound, and it's color-coded by the date of activity. The color code goes from blue on the 14th of January 2007 up to deep red at the end of the month. And you can see the tremor activity starts here south of the Puget Sound. It spreads a while bilaterally. It spreads about 10 kilometers a day, one of the numbers we don't understand. It quits to the south for a while, and I think we partly ran out of stations, but it did quit. And then it continued north till it hit the border, and then we lost sight of it, and it, I think, continued for a few more days where PGC could see it better than we could. But this is the general pattern. And you can also see the sort of contours where people used to think was the end of the lock zone, and the gap between those contours and the ETS. It may be this area isn't locked, but that's, again, the question of whether the lock zone is close to the Puget Sound or a bit further away. So we can start comparing different things. Now we can start comparing where does the tremor happen with where does the geodetically observed slip happen. And it turns out it's quite similar. So these contours from a paper by Aaron Weck show where the tremor is located. This was an average of 4 different events in the last few years. And the shaded region is where Tim Melbourne says the slip was geodetically, and they're very similar. If you look very carefully, the centroid of the geodetically inferred slip is a bit shallower than the centroid of the tremor, and other evidence from many other places suggests this might be a real difference. But to first order, the slow slip and the tremor are coming from the same place. Another way to look at this is from Japan, where we can compare tremor with tilt meter records. So all these little black sticks are counts of tremor, tremor energy. The thin black line is just the cumulative energy in the observed tremor. To compare that, we can compare that to this heavy gray line, which is the tilt. And what we see is very similar shape. The tremor is going great guns here at the same time as the tilt is showing that there's slip, and it ends at about the same time. So once again, there's evidence tremor and slow slip are basically 2 parts of the same process. A pattern which is surprising but seems robust comes from Anna Aguiar's work, again very recent. And what she's showing here is that the tremor has a moment. That's, again, the area of faulting times a slip. That's almost directly proportional to how long it lasts. So this comes back to the slope of 1 in that Ide plot I showed. The moment tends to have a particular rate of moment release, whether it's a 10 days, 15-day episode, or if it's just a 1 or 2 day episode. Again, not what we would have expected, but it's what we observe. This plot is meant to emphasize the continuity of tremor across all of Cascadia. There's actually a bit of a gap. It's kind of overemphasized here from the short time interval of Vancouver Island tremor, but there does seem to be a gap coinciding with where earthquakes are located under Vancouver Island. But the rest of Cascadia is just one continuous band of tremor, and this is, Aaron, the guy who made it, kind of making sure you look at it. But it's a very thorough process. We can also look at the time evolution, and Mike Brzezinski sent me this late last week after I asked him about a month ago. And it shows 4 years of tremor, and this, you'll watch this red line march to the right, and it's fascinating. At least I find it fascinating. So these are dots that shrink and disappear over the scale of a few days. What's particularly interesting is how they're kind of bursts of activity, even though they're hundreds of kilometers apart. And you can clearly see the 10-kilometer-a-day migration if you watch the individual spots evolve, and this is a nice episode. And then there's a quiet few months while we were all guessing at Washington this next episode would come later than it did. There's our major Puget Sound episode. And you can equally well make this figure from the GPS data. This one particular set of dots came from the seismic data. We can look at each of these segments along Cascadia and see the property of the characteristic recurrence interval. So if we look in northernmost California, it's clear these red lines, and you probably should draw a red line on this one, are evenly spaced at this interval of 8 months. These red lines in Oregon are evenly spaced with the greater recurrence interval. In the Puget Sound, it's just like clockwork, at least until we tried to guess when the next one would be, at 14 months. And further north, it's a little less regular. But this is, of course, much more regular than earthquake recurrence. We can also look at the evolution within an individual ETS episode. So here we have the episode in 2004 and 2005 in the Puget Sound. And you can look along strike. These are kilometers along strike, and these are days of time. And these two are very similar. They started in a similar place. They both went bilaterally. However, the next three were different and somewhat similar to each other, to the extent of having a migrating band of activity going this 10 kilometers a day, then having a later kind of reverberation of tremor back toward the beginning of where it first appeared and ending in about the same place. So these patterns are, again, somewhat repeatable, somewhat different. And in between the major episodes, we can also see tremor. So these two big black streaks are the tremor episodes in 2007 and 2008, but all these blue events are ones Ken found with Aaron Weck between those two events. And if we look at those in space, these black dots are the major tremor episodes. The blue dots are these tremor that are observed between the major episodes. And you can see the clear offset. They overlap somewhat, but on average, the inter-event tremor is to the right, down dip from the major episode tremor locations. Ken takes this further and looks at how many bursts of tremor there are as a function of how big they are. Specifically, he looks at how long they are and then converts that to a moment. But when he looks, you can make a Gutenberg Richter plot, just as you were asking for in the introduction, where there's a lot of short episodes and not so many long episodes. So it's just like earthquake, there's a size distribution of the tremor, even within this one segment that has fairly characteristic recurrence for the big events. And in fact, the big events are on this plot. They're not some special characteristic bump at a larger magnitude. So they're a lot like earthquakes in that way. Even with the B value, for those of you kind of more narrow seismologists, the B values are similar to earthquakes. We can look at how the tremor, episodic tremor and slip responds to stress. And this is a cartoon, really, Justin Rubenstein and I made a year or two ago. And the point here is that if you watch a tide gauge, you can watch the water go up and down, like the blue. And the tremor, it turns out, goes up and down, not perfectly correlated with the water, but close enough you can see the same minima. And in fact, if you do this quantitatively and Fourier transform the time series and look for the spectral peaks, there's clear tidal frequencies in the tremor. And this morning I learned for the first time from Jessica Hawthorne that the strain meter data indicates that the slow slip also has at least the 12-hour periodicity and probably the 24-hour periodicity as well as the tremor does. And I should say about the time we were seeing this, they were also seeing this in Japan and under Vancouver Island, and they've actually related the stressing more specifically to the tremor in those studies. So the tremor responds to small stresses is the point here. It's only a few meters of water, and the tremor gets stronger or weaker by tens of percent. Another example of tremor responding to stress is the excitation of tremor by surface waves from distant earthquakes. So this is the love wave from the Denali earthquake coming across Vancouver Island. There's a love wave here on the transverse component, a weaker Rayleigh wave later on the radial component. And if you high-pass filter some seismograms from Vancouver Island, you see this. 15 minutes. Am I going too slow? Okay, well, we're not quite done. Yeah, whenever the ground moves to the southwest, was the point I was making. We see a burst of tremor, another ground moving to the southwest, another burst of tremor. And in fact, we can even relate this to the stress. It turns out this surface wave is too long period to really stress the plate interface much. But this one's just the right frequency. It stresses it a lot, and it generates a lot of tremor. So the surface wave generates tremor immediately when the stressing is applied, and it quits when the stress is reversed. And to understand this, that this is the polarity that makes sense, here's our geometry. We're looking at Vancouver Island. Of course, Alaska is up to the north. We get an earthquake, a great big earthquake. The directivity sends a lot of energy down the coastline. Here comes the wave. And then the love wave basically wiggles the surface of the Earth while the depth is deep, it's fixed. So whenever the ground moves to the southwest, that's the sense of pushing the Juan de Fuca plate down. That's the sense of subduction. So it's the right pattern to see, tremor picking up when the ground moves southwest and quitting when the ground moves to the northeast. We were so excited by this, we got dwelled on two places, Vancouver Island and Parkfield. And Joan Gomberg, in another figure I saw a half dozen times this morning, another classic paper, even though it's only a few months old now, looked all down the San Andreas in California. She collected all the stations within 50 kilometers and found not only the two patches of tremor near Parkfield that we'd found, but found tremor 5 other places. So 7 places in California lit up with tremor that we know of so far when the Denali surface wave went through. So in fact, this is a much more common phenomenon than we thought just a year or two ago. Zhigang Peng has done a systematic study of picking up all the teleseismic waves going through Parkfield, and of the 40 biggest earthquakes, he found 10 that generated tremor, and they didn't generate tremor just in a spot or two. They generated tremor over much of the region below the seismogenic region within the lower crust. Again, quite a surprise, and I just learned this afternoon that they've found this kind of thing for regional earthquakes as well. And they found it several other places on the San Andreas as well now, too. That's been sort of reported for the first time today. And this is one of them. This is in the San Jacinto Fault, Justin Brown. There's a lot of stuff that's up here, but I'll just say with the San Jacinto Fault, there's great station coverage. They looked during the time of some big surface waves coming through, and they found tremor, or more specifically low-frequency earthquakes, located it very carefully, and it's clearly just under the seismogenic zone here in the southern San Andreas. So, okay, we've made it through most of this. I'll go to our dense array observations before finishing with more speculation. So we're back to this map of where the tremor goes in Seattle, near Seattle, and one time Ken Krager and I were sitting around talking about the thousands of Texan seismometers sitting in New Mexico looking for a use. So we got 200 of them and took them out and put them right here to record a tremor episode. And this is the map. If you look carefully, it's a topography of a mountaintop, a clear-cut mountaintop in the Olympic Peninsula. 84 stations. The aperture is about 1 kilometer. It's only vertical component stations. These Texans had flashlight batteries. We had to go out every 4 days and replace the batteries. It's kind of tedious, but it was only for a couple of weeks. So 84 sensors in a square kilometer. And so we rushed out there in March and we saw some tremor, but it turned out one of the minor episodes, but it was still a good training exercise. And then when the tremor actually happened in May, we did go out and we caught almost the entire tremor episode, and in the entire part of the time it was going under the array. So that was very good. And this is our 2 weeks of tremor in the form of a spectrogram from 0 to 20 hertz. And you can clearly see the kind of sporadic energy of tremor, and it was basically above the noise the entire time when you stack across an 80-element array. So just continuous tremor. All these horizontal spectral lines are cultural, although I wasted a lot of time hoping they were geophysical. This is an example of some cultural noise in a part. It's from 4.9 to 5.5 hertz, very narrow passband. There's something downtown that buzzes at 5 hertz within 1/100th of a percent. I think it's steam tunnels, but I'm not sure. There's something near the border that kind of wiggles. There's something that turns on only during the day and turns off at the night. There's some other stuff. That's all got to be cultural. However, and also you can see storms. This washed out area is a big storm. That's another storm. So we're not protected from the elements. However, this kind of more speckled banding here is tremor, and there's some here, and here are some LFEs Justin Sweet has been examining, which turned out to be quite interesting. Okay, we can learn some lessons from this. This is again, it was a weak episode. It was actually pretty far away, so it's a test of our sensitivity. And with our beam forming of nearly 100 stations, we could see a lot more than the traditional methods. In fact, I won't explain this in detail, but we could see 4 times as much tremor as the traditional methods. So this argument that tremor has a single amplitude is a little bit oversimplified. It does have weaker tremor and stronger tremor. And it also says that putting out a dense array is a very good way to get a clear look at the continuous activity. With this array, we were able to make a finer scale map of the tremor activity because we had quite good relative location of the tremor by beam forming this array. And this right-hand plot is the distribution of tremor inferred from the traditional envelope correlation methods, which have maybe 10 or 20 kilometer lateral errors. However, if we look with the array, for looking only in the circle, because that's all we have good resolution for, the tremor activity is much patchier. So it looks like there is fine scale structure in the tremor distribution. And we can also track it over time. And I'll start by comparing it to the figure Dave Shelley put in G-cubed a year or 2 ago, because he did it a very different way, where he can't track it continuously, but he can get good locations part of the time. So this will be a movie, so you can watch the blue line move. And what you see is tremor migrating. And the conclusion of his work, and of what I'll show for ours, is that this tremor actually migrates up and down dip at a speed of tens of kilometers an hour, in contrast to the migration along strike of 10 kilometers a day. So there's a lot of things that one needs to explain to fully understand tremor. So you can see all the flickering locations of tremor activity. Again, this is just projected onto a slab interface at some depth below the map view that you're looking at. And it just repeats endlessly if I let it. And this is our map. So for ours, we take every 5 minutes and figure out where the tremor centroid is. And then, and every minute, every 5 minutes, we can get a location. In fact, we can get every location every minute if we'd like. And so these symbols will start out as a big circle and then get smaller over time as the time of the tremor passes, and you'll see what's happening. What you'll see is this up and down dip migration under Cascadia, just as Dave Shelley saw under Japan. And the point is, it doesn't often stay in one place. It's usually moving, and it's usually moving pretty fast for some things, although, of course, much slower than rupture in an earthquake. So this is a day you're watching. And of course, again, the red line is moving along the envelope. You can see it's getting stronger and weaker pretty frequently, but it's more moving fairly continuously across the area. And then it just repeats endlessly, too. So we can break this down into sort of 12-hour segments. This is 12 hours per frame, so one day, and then the second half of the day, the second half of the second day. And these are all the tremor locations we found, and then these colored lines indicate the bands, the streaks that we can pick out that are particularly clear. What we see is the energy ripping back and forth, basically along the leading edge of the tremor distribution. Remember, this tremor is moving north at about 10 kilometers a day, so this is the leading edge on the up north side. And then 12 hours later, the edge is advanced, and the tremor is ripping back and forth now with the new leading edge. And that's the pattern we see throughout these 4 half-day pictures. So it's really a phenomenological description. Another way we can look at this is, how does a tremor move by comparing where it is every 5 minutes with the following 5 minutes? This is just differencing the locations for every pair of tremor locations we have. You can clearly see it's preferentially moving down dip and up dip, and not so much along strike. And for comparison, this arrow indicates the relative plate directions. And the lower plot indicates how far it is between the location in each set of locations separated by 5 minutes. And you can see it's moved a few kilometers every 5 minutes. So again, roughly 30 to, yeah, I think I've got maybe 3 more figures. Okay. And so again, it's about 50 kilometers an hour speed of this migration of the tremor. So just to really confound our potential for ever explaining this, there's another pattern that may be appearing, and that's longer distance jumps. So this is a part of the movie of Mike's that I showed. It's about 90 days in the middle of 2008, and this is distance along strike of the subduction zone. It's close to 1,000 kilometers, and you can see the tremors migrating 10 kilometers a day along here. Maybe it lightens up and lights up here and lights up there. I'm sure I can't convince you of that. And then it quits here, and then it kind of shows up here. You know, maybe that's a coincidence too. And in the meantime, there's an episode here, and then it kind of lights up here, and then it comes back over here. So, you know, only time will tell if this is just a coincidence, but, you know, those are pretty long distances. And this is a similar plot from Vancouver Island from a paper by Han Kao, where the tremor's here, and it quits here, and then it lights up here, and then it quits here, and then it kind of lights up over here again. And there are a number of other examples like this as well. And it's a little difficult to see how the tremor can know what happened 100 or so kilometers away, but, you know, we have to go by what's actually there. One way we're aiming to get more answers is an experiment we have in the ground. We intended to record the tremor last summer with this experiment, but it came 3 months early. So now we're aiming to record all the inter-event tremor and next summer's tremor, and perhaps the year after that if we can leave the instruments out that long. But the point is, here in northern Olympic Peninsula we have 8 arrays. So we can try to record our information redundantly and triangulate as well, and get an even clearer picture of what the tremor is looking like on the time scale of minutes to days. So just to recap, for those of you who didn't know what tremor is, I'll review. Basically, tremor is a kind of faulting that's showing up below the locked portion of many faults and above the freely slipping portion. Again, mainly shows up on major plate boundary faults, and we're mostly interpreting it as some kind of an effect of high fluid pressure, although just what, we're not sure. What we see is both rattling and slow slip. We have this unique scaling of the longer events just linearly accumulate moment with time. The amplitudes are very low. I don't think anyone's ever actually physically felt it. It's all instrumental. It begins gradually, it ends gradually, and it seems to respond to small stresses, and it seems to have a very small stress drop. And we can even influence its activity by the tides and by the passing surface waves. In terms of more details, it has these range of migration characteristics that, as I've said, we don't understand. It moves along strike 10 kilometers a day. It can move up and down dip tens of kilometers an hour. It flickers brighter and weaker every few seconds, although with some correlation times. And maybe it even jumps hundreds of kilometers. So we can try to explain this, but I won't pretend that I believe any of these explanations. We propose something with water pipes, and I know some people disagree with it. Turns out for the pressures down there and viscosity of water, even a couple of millimeters is enough that water could move those speeds, but still that has some conceptual issues. There's magma down there that may be playing a role. We heard about colliding creep fronts this morning from Alan Rubin that may contribute. You can think of all kinds of science fiction type explanations that are equally unlikely, perhaps, maybe even more unlikely. So where are we? I'd love to say we understand it, but the point is we are going to understand this, I think, and we have a lot of evidence. This is the last slide. Oh my God. Wow. It said till 6 in the schedule. It is 6, right. Okay. So we're gathering evidence, the relation between ETS and earthquakes. We're seeing how the geology relates to the area with the ETS, and we're able to watch in ever more detail how the episodic tremor and slip unfolds. And so we have a lot of reasons to understand this. It may indicate seismic hazard. It may help light up where the asperities are locked. And it may help us understand the mechanics of subduction. And I guess I really better quit. Sorry about that.
That was great. This is great stuff. Well, before people leave, I will actually open the floor for a few questions if there are some. But before I do that, people are leaving. There is a joint reception for seismology and tectonic physics that starts in half an hour at 18:30 until about 8 o'clock. And it's in room 304. So that's in this building, Moscone South. It's on the 3rd floor. And with that, a few questions. Now, there is no microphone, so I would like to ask the people that ask questions to be loud, and I would like to ask John to repeat the question in the mic.
Okay.
Please.
John, wonderful summary. I'm curious about one thing. You talk about these complex phenomena, tremor and other things, but you couch, at least in some cases, in terms of an old model of lock versus slipping. Lock used to be defined by no high-frequency earthquakes. So, do you really think it's lock versus freely slipping, or is it something else?
I really don't know what it is, so I'll just say I'm not sure. Oh, yeah, I don't understand the question, in fact.
Thanks, Chris. Are there more questions? I don't see it. So, well, with that, I would like to thank John Vidale again for a very exciting talk, very exciting results. Thanks, John, and congratulations.
Okay, good.
And so